Assalamualaikum. Hi. We continue with the rates of metabolic oxygen utilization. In designing bioreactors, we frequently use correlation of data to approximate the situation in order to establish whether the slowest process step is the oxygen transfer rate or the cellular utilization of oxygen. The maximum possible mass transfer rate is found by setting CO2L equals to 0 when all oxygen entering bulk solution is assumed to be rapidly consumed. So the maximum possible oxygen utilization rate can be calculated from the equation of oxygen uptake rate equals to cell concentration times the maximum specific growth rate over the yield coefficient of cell concentration over oxygen consumed. So X is the cell density, Y is X over O2, the yield coefficient based on oxygen consumption. At steady state, there can be no accumulation of oxygen at any location of fermenter. So therefore, the rate of oxygen transfer from bubbles must be equal to the rate of oxygen consumption by the cells, meaning that oxygen transfer rate will be equivalent to oxygen uptake rate. So the equation for the oxygen transfer rate equals with the equations of oxygen uptake rate. The maximum cell concentration, it can be supported by the oxygen transfer in the fermenter when CO2L is equivalent to 0. Therefore, the equation will become KLaCO2 star, which means the oxygen dissolved, saturation of the oxygen dissolved in the liquid over QO2 equals to XM. Let us see the factors that affect the oxygen transfer in the fermenter. The rate of oxygen transfer in fermentation broth is influenced by physical and chemical factors that will change the KL value, the A value, or the driving force for the mass transfer, which is CO2 star minus CO2L. CO2 star is the saturated dissolved oxygen in liquid. CO2L is the current or the recorded oxygen dissolved at that time. The typical KLa value, it will be between 0.02 per second to 0.25 per second for production scale fermenters. The factors that affect the oxygen transfer are bubble size, gas pressure, the presence of the cells, and the temperature and others. We'll look into it later. Okay, let's start with the bubble size. It's the major goal in the bioreactor design because of the high level of gas dispersion is required. Small bubbles, it provides more interfacial area, which is A. Therefore, it have a correspondingly slow bubble rise velocity and it stays in the liquid longer if we have this small size of bubbles, and it will allow more time of oxygen to dissolve in the liquid. With a small bubble size, it creates high gas hold-up, which is defined as the fraction of the working volume of the reactor occupied by the entrant gas, given by the equation in the notes here. And epsilon is the gas hold-up, Vg is the volume of gas bubble, Vl is the volume of liquid. Next factor is viscosity. In the viscosity situation, the KLa, it will be decreases with increasing liquid viscosity. Increasing viscosity will increase the thickness of the fluid boundary layers that surround the bubbles, which make increasing of the resistance for the bubble to transfer. Dampens turbulence. Okay, it changes the size and structure of the ventilated cavities at the impeller blades, which later it reduces the effectiveness of gas dispersion. Therefore, we need to avoid this increment in terms of the viscosity in the fermentation. So the plots here, it shows the effect of solution composition on KLA in the stirred tank reactor at a constant gas flow rate. This figure shows a flow pattern and how the bubbles disperse in the fermentation media with increasing stir speed and gas flow rate. As you can see, when the air is sparged different gas flow patterns, it will develop different patterns depending on the relative rates of gas input and stirring. You can read more on page 203 and 204 in the Schuler and Cargie textbook. Okay, so meaning that this stir speed and gas flow rate, which is aeration, it does give the effect in oxygen transfer in the fermenter. By increasing the stir speed, it will improve the value of KLA. Obviously, increasing stirring speed can give a rapid result in the increment of the KLA. Agitation, which is the stirring speed, it will improve the KLA through three ways, which are the first one, by chopping up the air stream into small bubbles. Then the agitation increases the interfacial area in the fermenter. Second one is by circulating the liquid in swift eddies, which delays the normal escape of the bubbles. And the final one is agitation will create turbulent shear, which reduces the thickness of the liquid film. Impeller flooding occurs at high gas flow rates unless the impeller is able to disperse all the gas impinging on it. Flooding should be avoided because an impeller surrounded by the gas no longer contact the liquid properly, meaning that the gas that surrounded the shaft and the impeller, they will not be in contact with the liquid in the fermenter, which results a poor mixing gas dispersion. Therefore, we need to avoid the flooding. This is the plot of dependence of KLA on operating conditions in the agitated tank, the stirred tank reactor. The first graph, the LHS, is the effect of stirrer speed at constant gas velocity, whereas the second graph, RHS, is the effect of gas flow rate at constant stirring speed. The symbols represent fluid at different viscosities. The black dot symbols, represent the fluid with higher viscosity. As you can see, KLA is reduced with increasing viscosity, but KLA is increasing with increasing stirring speed. However, if you look at the effect of the gas flow rate at a constant stirrer speed, not much significant change in the value of KLa, but somehow in less viscosity fluid, the KLa is greater than that of the higher viscosity. Okay. This shows that the stirring speed, it gives a rapid result in terms of, in order to increase the KLa, the mass transfer in the fermenter rather than the aeration. But still you can use the aeration in order to increase the mass transfer, but you still require the stirring speed to be increased in order to have a better mass transfer in the fermenter. We can also use an antifoam agent. So most of cultures, it will produce a variety of foaming during the fermentation. So this foam build up in the fermenter is very common, especially in the aerobic system, because of we have this aeration through the sparger. Okay, foaming causes a range of reactor operating problems. So foam control is therefore important in order to have a better mass transfer rate inside the fermenter. Therefore, in order to reduce this foam, you can use a special antifoam compound called as antifoam adjuncts, which can reduce the foam build-up in the fermenter. These antifoam agents affect the surface chemistry of bubbles and their tendency to coalesce and have significant effect on the KLa. It will break up the bubbles, the foaming, and reduce the thickness of the foam. These are the figures that shows the effect of antifoam concentration on surface tension and KLa. Okay. So decreases in surface tension reduces the bubble diameter with increasing. Okay, in terms of antifoam, it increases the values of A. However, increase in antifoam concentration, it lowers the value of KL as it reduces the mobility of gas-liquid interface. Effect of temperature on the oxygen transfer. Increasing the temperature, it causes solubility of oxygen to drop. As temperature increase, the solubility of oxygen will decrease, so that the driving force for mass transfer is reduced. At high temperature, diffusivity of oxygen in the liquid film surrounding the bubbles is increased, resulting in increase of KL. For temperatures 10 degrees C to 40 degrees C, an increase in temperature is more likely to increase the rate of oxygen transfer. Temperature larger than 40 degrees C, the solubility of oxygen drops significantly, adversely affecting the driving force and rate of mass transfer.